All right, Calc PC, Unit 1, Day 6, Exponential Functions and Logarithmic Functions. So, exponential functions, definition is a function whose growth over time is proportional to its current population or amount or whatever. So, rough sketch of an exponential, you guys should know this. So horizontal asymptote, y equals 0, goes through 0, 1, and looks kind of like that. So, anyways, this right here, growth is a derivative. It's the slope, right? So this is this can be translated into a differential equation, diff eq, de, whatever you want to call it, diff eq. So the growth, so we could say dy dt is directly proportional to k times the current population. So that's translation of those words into a calculus. And we're taking the derivative with respect to time. This is a constant of proportionality. This is the population. And last year we learned in Calc AB how to solve differential equations. We have to separate the variables by multiplication and division to get things from one side to the other. Integrate both sides. Natural log the absolute value y, kt plus c. We could find the c value. Well, a lot of times we know the initial amount, y sub 0, at time 0. So c would equal natural log the absolute value of y naught. And so then we could rewrite it, natural log of y equals kt plus natural log of y naught. And then we could solve for y. So we exponentiate both sides. Let's cancel each other out. We use rules of exponents. This is e to the kt times e to the natural log of y naught. Get rid of the absolute values to plus or minus now. Y naught's generally going to be a positive amount, so those cancel each other out. We can just put that in front. And then the plus or minus just has to do with whatever the initial condition is, which in general in these applications is positive. And so we just derived the exponential growth equation that you guys were taught back in Algebra 1. Some other questions we could ask, we say how long to double the population, so that's doubling time. So you could take, let's say we start with 1,000, then doubling would be at 10,000. Now you could just do y naught and 2y naught, and the y naughts would cancel each other out when you tried to solve for the doubling time. Here, if you divide by 1,000, guess what you get? 2. Whatever it is, you're always going to get 2 if you're doubling it. So then you could take natural log of both sides, and that would just give you kt. And so then t equals natural log of 2 over k. Now, natural log of 2 is 0.693 over k, and if we were to write them as like a percent, that'd be 69.3% over k percent. K is a growth rate, which is often described as percent. And so this is the doubling time. So in some of your classes, you guys might have actually used this before, but this is the, say, rule of 70, because that's about 70, and it says that doubling time is 70 divided by k, roughly. So for instance, if it were 2% growth, then the doubling time would be about 35 years or whatever. So rule 70. Also, just as a note, and we will be studying it this year officially, as a more realistic growth model is logistic growth model. And logistic growth model has a horizontal asymptote, and it kind of looks exponential at first, but then it approaches what we call the carrying capacity, which is sort of a ceiling of realistic growth. Like, things can't just grow unbounded. So it, at half the carrying capacity, which we usually denote with a capital N, it goes concave down. It keeps growing. The slope is positive, but then it approaches this other horizontal asymptote. And this happens at this inflection point, which is also the greatest growth experienced. Anyways, in reality, populations, things level out, run out of room, run out of resources, etc. Okay, so that's just a little background on differential or exponential functions. So now let's just study real quick the basics of the graphs of them. So if the base is greater than 1, which is the case here, that's e, but that's a special case. We can just plug some values in here. So here's an example, like b equals 2. So 2 to the negative 2, or 2 to the negative 2 is 1 over 2 squared is 1/4. Right? 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. And if you're to graph these, it kind of has, it'll look like this. Yeah, it'll have a horizontal asymptote, because the more negative values put in, the smaller the number gets, but it never gets to 0. They always go through 0, 1 for the y-intercept, unless some changes have been made to the graph. On your homework today, I'm going to expect a graph with the intercept labeled and the asymptotes. And then you'll be asked, is the graph increasing or decreasing? So this one's increasing. Is it concave up or down? It's concave up. What's its range? 0 to positive infinity, interval notation. And what are the equations of its asymptote? So this is going to be y equals 0. So it needs to be y or x for asymptotes, because their equations aligns. But that's the basics there. Now, how does it change if you have a base between 0 and 1, for instance, like 1/2? Well, we could plug these in. 1/2 to the negative 2 would flip it and be 2 to 2 is 4. 1/2 to the negative 1 is going to flip it. It's going to be 2. 1/2 to 0 is 1. 1/2 to 1 is 1/2. 1/2 to 2 is 1/4. You notice over here we're getting all the same values, but they're going backwards. And so the graph has the same shape. It has the same values, but it goes downward. So this is like a decay function. And I'm going to ask the same questions on your homework. Is it increasing or decreasing? You would say, well, it's decreasing because it's going down. Is it concave up or concave down? It's concave up. Its range is 0 to positive infinity, and the asymptote is y equals 0. So this is the same stuff I'm going to be asking. Now here's here's the way I like to deal with these. Instead of trying to remember, oh, if it's a fraction, it does this. I think of S=1/2, and I think, well, that's 2 to the negative 1, which is 2 to the negative x. And guess what a negative inside a function does? It flips it across the y-axis, and you get that graph, right? So I kind of like to use that because that's something you should already know. So it kind of cuts down on stuff. So here's a couple quick examples. This is the way I want you guys to graph these graphs of functions. Start with the parent function. It goes through 0, 1, has an asymptote of y=0, and it looks like this. Now I should have drawn a light. Now the negative, we want to work from the inside out, flips it across the y-axis, and now it looks like this. The +2 moves everything up 2, so the y-intercept is now at 0, 3. I want to keep track of that. The asymptote is now at y=2, and your final graph looks like that. And then you're going to answer the questions. It is decreasing, concave up, range is 2 to positive infinity, and the asymptote is y=2. So there you go. Here's another example. Now, like I said, I personally would like to think of this as negative 2 to the negative x minus 1, because 1/2 is the same as 2 to the negative 1, and the rules of exponents, all that stuff. So I'd start with y=2 to the x as the parent function. And label all this stuff, make it light and dashed. Then the negative on the inside flips it across the y-axis, right? The negative in front flips it upside down. So now you're down here. The -1 shifts everything down 1. So asymptote goes down 1 to y=-1. Your intercept goes down to 0, -2. And your final graph looks like that. So I'm going to say that it is increasing, concave down, range is negative infinity, -1, smallest greatest, and the asymptote is y=-1. Now you got to make sure you put the y equals with your asymptote. So that's what we're doing with those. So in that, we'll take a look at logarithmic graphs, logs for short, and they're inverse functions, exponentials. So these are closely related to what we were just talking about on the front. So just to help us with this example to show the relationship, let's just do this exponential with base 10 first. So 2 to the negative 10 is, or 10 to the negative 2 is going to be 1/100th, 1/10th, 1/10, 100. And this graph looks just like the graphs are graphing on the other page. And I'm not really looking for anything more specific other than making sure you get your asymptote and your intercept correct. So that's your graph. Now, if we go the other way, now the way logs work is it's asking you. Now, if you don't see a base, that's base 10. That's called the common log because our number system is base 10, so it comes up a lot. It's handy. But it's asking you, what do you, when you see this log base 10 of x, it's asking you, what do you raise 10 to get x? 10 to what power equals what's inside? So when I look at this, I say log base 10 of 100th. I say 10 to what power give me 1 over 100? Well, that would be 10 to the negative 2. 10 to what power gives me 1/10? 10 to the negative 1. 10 to what power gives me 1? 0. 10 to what power gives me 10? 1. 10 to what power gives me 100? 2. That's the way I think of it. Now, the interesting thing you might see right here is that I have all the same values, but the x's and y's are switched, which is something that always happens with inverse functions. The x's and y's get switched. It's actually something we use to find inverse functions. Now, visually, what happens when you switch x's and y's, it's like reflecting across y equals x. And this is always true. So 0, 1 becomes 1, 0. Horizontal asymptotes y equals 0 become x equals 0, right? Everything at y was y becomes x, everything at x becomes y. And when you draw your graph, it should look like a mirror image across that line, y equals x. So, and then we're going to ask same kind of questions on the homework. We say, oh, well, it's increasing and it's concave down, and its range is negative infinity, positive infinity. The asymptote is now a vertical line, x equals 0. So, some other interesting things about inverse functions in general. This is something we talked about last year also in calculus. So the fact that the x's and y's are switched, the fact that it's a reflection across y equals x, that's stuff you should have seen in previous classes. But I kind of like to use exponentials and logs as a good generic pair of inverse functions. So, let's say this is y equals 2 to the x. Well, then this would be log base 2 to the x. Let's say that there's a point on this graph 4 comma 16. Well, then there's a corresponding point on the other graph at 16 comma 4, right? So that's always going to be true. Now, something interesting with the slopes happens. So if you draw a tangent line, and let's say we did this decently, then what should happen is that they cross each other on that y equals x line. They're definitely not parallel. They're not necessary. There will be one special pair that is parallel in general, no. Perpendicular, no. But what happens is, I'll show you in a second. Let's see. Just to remind you, y equals 2 to the x, the derivative of that is itself, right? E to the x is e to the x, but with an extra natural log of the base, right? So e to the x is a special case where it's e to the x times the natural log of the base e. Well, natural log of e is 1, and so you just get y prime equals e to the x. So that's a special case that we've memorized. And then natural log of x, the derivative of natural log of x is 1 over x. That's a special case because in general, if you have log of any base, the derivative is going to be 1 over what's inside, but then times 1 over the natural log of the base. So in this situation right here, the slope at this point right here, y prime of 2 to the x with a 4 plugged inside is going to be 2 to the 4th natural log of 2. And then this graph over here, you're going to plug 16 into the derivative log base 2, and so it's going to be y prime 16 equals 1 over 16 times 1 over natural log of the base. Now what you'll notice is that the slopes are exactly, this is 16 by the way, 16 natural log of 2. The slopes are just the reciprocals of each other, which totally makes sense. That one's just the other one flipped upside down because everything that's x becomes y, everything that's y becomes x. So rise over run, rise is change of y over change of x. Well, the change of y now becomes the change in x. The change in x becomes the change in y. And so the rise over run flips and you get the reciprocal. So graphing log functions. I usually don't like to try and memorize it unless I'm really good at it from doing a lot of them recently. But if it's been a month or so, it's easy to mess these up. I would usually start with the corresponding inverse function exponential version because I'm really good at those. Right? I mean, y equals e to the x. I mean, I've been doing those since algebra 1, right? And so that's easy to remember. And then we flip it over y equals x. I think I kind of messed this up. Should probably be a little mistake. So it's going to be 1, 0. It's going to have a vertical asymptote x equals 0 instead. And it's going to look like that. So that's usually the way I'm going to do it. And then, of course, you'd answer. Now, natural log, by the way, is log base e of x. It's a log. It's the natural log, though, because that's the natural number as its base. So this one right here, I'd probably go and just, start with the exponential y equals e to the x, and then flip it across y equals x. So it's going to be 0, 1, 0, and asymptote is going to be x equals 0. And then I get work from the inside out. So the minus 2 moves everything right to, including the asymptote. And so we're at 3, 0, 3, 0 now. I want you to keep track of that. Keep it labeled on your graph. I guess I never even graphed it. So this is our new graph. The negative on the outside flips any graph upside down. The plus 1 moves any graph up 1. So now we're at 3, 1, and arrows on the ends, darken it in, keep the rest of the stuff. That's your work. We'll answer the questions that we've been answering. We say, oh, well, it's decreasing. It's concave up. The range is negative infinity to positive infinity. And the asymptote is x equals 2. So you'll be doing that on the hump. Okay, now we need to talk about domain. Domain for any function is important, but logs are notorious because the natural log graph only exists for positive x's. X equals 0 is a vertical asymptote. Negative x's just don't make sense. You can't raise a positive base to some exponent and get a negative answer. That just can't happen. So we can only take logs of positives, not negative, not 0. So we need to keep that in mind. Whenever we're dealing with a problem that involves logs, we've got to make sure that we know what values are even possible from it so we don't give answers that are impossible. So in this one right here, x has to be greater than 0. We're going to go and write our domains in interval notation usually. Okay, this one right here, the inside has to be greater than 0. So this would be the work that you would show. And of course, change it to interval notation. Now, sometimes it could be more complicated. It might be a polynomial, might be a rational function. It could involve trig. Now, this is now one of those rational inequality problems that we were doing before. So x equals 0 is a root, x equals 3 is a vertical asymptote. We do a line check. These are both open dots. We test a number, x equals 4, true, false, true. And so our domain is negative infinity to 0 union 3 to positive infinity. All right, so you might have to do some other work. Log rules, gotta know your log rules. We can always change a log into exponential form. B to the A equals N. The answers to logs are exponents. The A is an exponent. Natural log is log base E of X. There's a log rule where if they have the same base and they're being added, you can combine them together into a single log and multiply their insides. If it's subtraction, you can combine them in a single log where you divide the first one by the second one. You can also move exponents out in front. It's called power. So you can do that. You can move them out front as a coefficient. Log base b of b is 1. What do you raise b2 to get b? Log base b of 1. What do you raise b2 to get 1? 0. No matter what b is, the only way to raise something to a power and get 1, unless the base was 1, which is a silly log, is to raise it to 0. Natural log of e is the same thing as log base e of e, which is 1. Natural log of 1 is the same thing as log base e of 1, which is saying what do you raise e2 to get 1? 0. Anytime you have log or natural log of 1, it's 0. And then there's a change of base formula that says if you have a certain base and you'd like another base, like say base 10 or base e, because your calculators do those nicely. So like if I already changed it to log base 10, I would take it of the new log with the new base of what was inside, but then I get divided by log with a new base of the old base. So we would usually write this one simpler because base 10 is the common log. But those are all the log rules. Now, maybe we can try a couple problems real quick on the homework. There are 2 worksheets for tonight's assignment. And one's for exponentials and one's for logs. So I thought we could try. So there's Unit 1, Assignment 6. We'll call it A for exponentials. And there's Unit 1, Assignment 6. We'll call it B, and that one's for logs. Okay, so on the second worksheet for logs, problems 13 and 14, how do you solve log equations? So this is something you guys have learned before without a calculator. If you have a bunch of logs with all the same base, then you want to combine them together into a single till log equals a log. So one strategy is to get a log equal log and then set the insides equal to each other. Now we got to use some of those log rules. This is going to be 6 over 12 equals natural log of 3x. And so now, logically, natural log of something equals natural log of something. The insides have to be the same if this is true. And so then we get x equals 1/6. So that's the way you solve a log equation that has a bunch of logs. Now 14 is a little different because you don't have logs over here. So if you have log of something equals some number or something, then what you should do is change it to exponential. So 6 to the x equals 216. And now this problem becomes like a problem that's actually on the previous assignment to this one, the exponential one. And the way you do this is to try and make the bases the same. Now 6 can't be made to any smaller base, but I think this is 6 to the third. You could check it if you want. 6 times 36 is 36. Carry the 3 to 18 is 21. So if you make the bases the same, then you can set the exponents equal to each other. Similar idea to having 2 natural logs equal to each other. So these are the 2 different strategies that you're going to be using on problems 12 to 22. Okay? You are allowed to use a calculator on problems 23, 24, 25, 26. So try both these worksheets, assignment 6A and 6B. One's exponential, one's logs, and check your answers.